real-time dynamics of doped helium nanodroplets, density versus atomic. So you have 40 minutes, and I will tell you when we end, 5 minutes before the end.
Thank you. Okay, so I'm really happy to be here. Thank you also to David and Sabine, who have done most of the work. And so the people who have been involved in the things that we'll present today are Ernesto Garcia Alfonso, who's doing his thesis right now. I will be also showing some pieces of the work by Patricia Windelton-Bergen, who was a postdoc, and some older work by David Bonomo, and everything is a collaboration, or most of the things is a collaboration with Manuel Barranco and Marti P at the University of Barcelona, and Fausto Cagnoni at Milano. Yes, I forgot. So mostly I'm going to talk about helium nanodroplets. Just a quick reminder, there are clusters of several hundred to several hundred of millions, or even more nowadays, helium atoms, which are built in a cooled supersonic expansion. And then they are usually made to go through a scattering chamber where they can pick up dopants. And they are studied by the usual means of molecular physics, laser excitation, mass spectrometry, etc. They have been determined to have a temperature of about 0.4 Kelvin because most of, more or less everyone has the same setup for the formation of the droplets. And the reason why people became interested in studying them is that at 0.4 Kelvin, you are about here in the phase diagram of helium, and this is in the middle of the superfluid phase of helium. And so, of course, one of the first questions was, what does it mean to be a superfluid in a finite size system? In particular, the properties that will be relevant today are frictionless motion. So this has been shown on molecular rotation, which is almost like free molecular rotation. And also the existence of a Landau critical velocity below which molecules or dopants can move without friction inside the droplets. Another very interesting property is the very high heat conductivity, which means very fast energy dissipation. And so for molecular processes, collisions, reactivity, of course, it's important. And there is also the existence of quantized vortices. So I will not explain in detail what quantized vortices are, because it's a whole lecture in itself, but we'll see some of them on the way, some properties. So that means helium nanodroplets are also some kind of, people have called them nanolabs. So it would be even a flying nanolab. So it's kind of a joke, but it stresses some important aspects of their properties. So basically, the pickup by the helium droplets is extremely efficient. So it's much easier than trying to put atoms or molecules inside bulk super helium, which is more difficult. And then the clustering, because of the very high heat conductivity, is also very efficient, but it also gives some surprises because then you get some kinds of exotic configuration because of the very fast cooling. One of the early examples was clustering of HCCCN, whatever the name of that molecule is. It has a large dipole moment. And that means at long range, they tend to align and form a chain. And when they actually come into close contact, they don't have enough energy anymore to reorient, to flip, in order to form the more stable isomer, which would be head to tail. And so they formed very long chains like this, up to 10 or 12 molecules, which detected because of very large dipole moments. So we get exotic configurations, and we will see some of that today. And quantum vortices. So quantum vortices, very quickly, they have helium doesn't really, superfluid helium doesn't really rotate. All the rotational angular momentum is concentrated in the vortex line or near the vortex line. And the vortex line is actually an empty line. And so the way they have been detected initially, the first time, was in the group of Villisov in Los Angeles. And they visualized them by doping them with rare gas atoms or silver atoms. And in particular for silver atoms, they would then make the droplets land on a carbon screen. And then they got these nice filament-shaped clusters, which were a trace of the vortex lines. So this is what we're going to show today. I'm going to show some clustering with the helium vortex. And I'm also going to show another type of experiments, which would be the fate of an excited alkali atom inside a helium nanodroplet. So what are we facing exactly? Well, as I said in the introduction, there are many atoms. So if you want to do something interesting in order to be able to compare with the experiment, you need to be able to treat at least several hundreds of atoms. Of course, it's helium, so it's quantum. We want to study real-time dynamics. I will show you some comparison with femtosecond experiments. And if some superfluid properties are present, which we hope they are, then you have to treat boson exchange. So of course, that means you cannot do it. And so you have to resort to approximations. So the current approximations that have been tested are zero-point average dynamics. I'm going to tell you a little bit about it, so I won't explain it now. Also, ring polymer molecular dynamic or centroid molecular dynamics, which are different versions of based on path integrals, and Helium Dft and its time-dependent version, which I'm also going to explain now. So Helium Dft, because there are too many atoms, you can decide to work with the density of helium rather than having to treat all these individual atoms. And that's the idea behind Helium Dft. It's the same idea as electronic DFT, but you work with the helium density instead of working with the electron density. And so you write the total energy as a functional of the helium density. You have a first term here, which is the kinetic energy of independent particles at 0 Kelvin. And the rest is hidden inside the functional. And then if you have a dopant, you add an external potential if the dopant is treated classically, which is what I'm going to show today. There's also something else if it's quantum, but it's not very different. So just to show you the form of the density that has been improved year after year. So this is now the final form. It's actually, the parameters are, so there's a Lennard-Jones that you recognize here to represent the helium-helium interaction. And then there are other terms to correct for exchange correlation, to correct for the kinetic energy. And the parameters have been fitted in order to reproduce bulk superfluid helium properties, in particular the excitation curve, so dispersion curve. So that's why it's also very accurate for dynamics. So how do we use that? When we want to study an equilibrium configuration, we minimize the total energy with respect to a pseudo wave function, which is just the square root of the density. And that gives us an equation here, which looks very much like the Schrödinger equation, except you have this term here, the derivative of the functional, which makes it nonlinear. And then this mu here is not an energy, but it's the chemical potential, because you add the constraint that the total number of helium atoms is constant. Okay, here the potential that are inside here are taken as a sum of pairwise interactions, and they are taken from the literature. So when you solve this, you solve it by imaginary time propagation on a 3-dimensional grid, Cartesian grid actually, and that gives you the equilibrium density for the system that you are considering, obtained as a square of this pseudo wave function. And this is what will constitute the initial conditions for the dynamics. Okay, so just to show you a result of the configuration of a static Helium Dft calculation, this is the equilibrium configuration for the rubidium atom. The alkali atoms don't go inside the droplets. All the others will go inside the droplet, but the alkali atoms, because of their external valence electron, they stay on the surface. The electron-helium interaction is repulsive, but they remain bound. They have on a dimple, a distortion of the surface here. And so just to give you some orders of magnitude, this is a 1000 helium atom droplet. So the radius is about 22 angstrom, and the rubidium atom sits about 4 angstrom above the surface. This is the value of the bulk superfluid helium density, 0.0218 per angstrom cube. This is mostly everything that is orange color. So most of the droplet is at the same density as the bulk superfluid helium. And just this corresponds to an average helium-helium distance of 3.6 angstrom, which is much larger than the equilibrium density, equilibrium distance, sorry, of the helium-helium interaction potential. Okay, so then we want to study absorption spectra. We want to do some dynamics. So we have to go to excited states. In the excited states for alkalis, it's easy, between quotes. We use just to describe the interaction between the excited rubidium and the rest of the droplet. We use a diatomic in molecule model with one effective electron for the alkali, the valence electron. And we add the atomic spin orbit to it in order to describe the spin orbit interaction. So we end up having a description of the electronic state projected over the different orientations of the p orbital of the excited atom. And so when we want to calculate an absorption spectrum, we take a large number of configurations, and for each configuration, we sample positions for each of the 1000 helium atoms, following the equilibrium density. So it's an important sampling in order to reproduce the quantum fluctuations. For each of these configurations, we calculate the vertical transition energy from the ground to the excited state. And then we get the spectrum as a histogram by binding all these energies. So I'm showing here, for instance, the excitation. So this 5s to 5p absorption spectrum of rubidium on a 1000 helium droplet on the left-hand side, and 5s to 6p on the right-hand side. Sorry. The top plots are the experimental spectra. They look a bit strange because I compressed them to be on the same scale as the calculations. And the curves are just the absorption spectra. So it's shifted with respect to the atomic lines, and it's also broadened because of quantum fluctuations. And this is what is reproduced by the calculations here. So the agreement is rather good for 5s to 5p excitation, but the shifts are too important in the case of the 5s to 6p excitation, which probably means that the potential that we are using for the 6p excited states are too repulsive. So they are too, they give a blue shift that is too large. Okay, and now for the dynamics. In this case, the dynamics of an excited alkali on a helium droplet. Again, we have the total energy as a function of the density. And the added term is here the mean field, so the helium interacting with the mean field of the excited rubidium, which is just the wave packet here. So when you minimize the action with respect to the pseudo wave function, the pseudo wave function now becomes complex because it's time dependent. You get coupled equations, one for describing the time evolution of the pseudo wave function, so of the helium density, which again looks very much like a Schrodinger equation, but now the time dependent Schrodinger equation. You still have this nonlinear term here. Oops, there's a missing part here, but just says that rho is a modulus square of the pseudo wave function. And then the time evolution of the wave packet, which describes the electronic excitation. And the third equation is for the rubidium atom itself, which is treated classically. So you recognize a gradient of the mean field. Okay, so I'm describing the simulation of an experiment in which there is first a laser that excites the rubidium on the top of the helium droplets to 5p or 6p level. And then after some time delay, there's a second laser that comes and ionizes the rubidium atom. So the first atom, because of the excitation, because in the excited state, the valence orbital becomes broader and more diffuse, it will eject the rubidium atom. And the second one, because it ionizes the rubidium atom, it creates an attractive interaction between rubidium plus and the droplets. And then it will tend to come back and get solvated. But this is only possible if it hasn't moved already too far. So here I'm showing the case where the time delay is 50 picoseconds. So you see at time excitation, the rubidium starts escaping. And when it turns red, it means it has been ionized, but it's already too far. It has already too much kinetic energy. So it's actually escaping. Up. Come on. Okay. Now, the other case that we studied here is the time delay of 20 picoseconds. And you will see the rubidium turning red earlier here. And now you can see it slows down because it feels the attraction by the helium and turns around and will get solvated. So there is some critical time delay, which separates a regime where the rubidium will escape and the time where the time delays where it will turn around and get solvated. They called it, experimentally, they called it a critical time delay. And this is what we reproduced with our calculations. So we get a pretty good agreement. I'm not showing all the details, but because I will come back to it later, we get a pretty good agreement, except in some cases, and I will go back to these cases. The other example that I wanted to show you is the formation of a cluster inside a helium droplet. So now the additional term is just the sum of dopant helium interactions. This is all in the ground state now. And if there are several dopants, you add the dopant-dopant interaction also, of course. This is all atom-atom interactions. So I hope there are not quantum chemists too in the room. So for the dynamics, again, same procedure. You minimize the action with respect to the pseudo wave function. And now you get, again, time-dependent equation for the pseudo wave function. So the time evolution of the classical equations for the dopants, which are just a gradient of the interaction potential. So this we solve with the Hamming's predictor corrector propagation. Well, this is very classical. And here I'm showing the case of 6 argon colliding at about the room temperature kinetic energy at 300 Kelvin in the droplets. You see 2 views, one is from the side and one is from the top. They are identical because in this case, the droplet is spherical, but we'll see another case where it's not. So you see the three pairs of argon atoms approaching from opposite sides on the X, the Y, and the Z axis. Okay, and if I can make it start, you see as soon as the argon enters the droplets, they get surrounded by a shell of helium atoms because the helium-argon interaction is attractive. They go to the center, they meet because they're attracted to each other, but this shell of helium atoms stays in the way, so they cannot really form direct bonds. And this is even clearer here. This is a cut here on the right-hand side, a cut at the end of the simulation through the XY plane. And on the left-hand side, you see what you would expect if the hexamer was solvated inside the droplet. So the gas phase hexamer, which is a bipyramid with a square basis. So you see the close contact of the four atoms that are in the XY plane. And here you see the helium density that has gotten in the way and is kind of frozen there. So it prevents the argon to form argon-argon bonds. So now with vortices, since I talked about vortices, here is a droplet with 6 vortices. You see it by transparency. Here a side view and here a top view. So you see the presence of the vortices flattens the droplet. That's why now you see different. The vortex lines, as I said earlier, they are empty. They're empty lines. And we again start from the same configuration, 3 pairs of argon atoms approaching from opposite sides along the X, the Y, and the Z axis. Again, come on. Oh, that was too fast, sorry. Wait, start again. Now, you see again, as soon as they enter this shell of helium that's forming around it, you see that they are attracted to the center. There's a vortex line in the center. And then you see one got stuck on one of the side vortex lines. But after a while, it detaches and will also go towards the center. And again, you see that the cluster that is formed is not what you would expect from a gas phase hexamer. At the same time, there's a helium shells, and also wherever one argon atom gets into contact with another one, they will stay there and not try to find, they don't have enough kinetic energy to try to find the most stable isomer. Okay. So as a quick summary of the Helium Dft and time-dependent Dft, it does help. It makes a good job in reproducing clusterization, because even if we don't form the most stable isomer, which is not what is formed in the experiment after all, it does reproduce clusterization along a vortex line. The atoms are attracted to the vortex lines. And then in the case of photodissociation, it does reproduce critical time delays, except in some cases where there is actually some helium-induced electronic transition. And there are a few cases, even with the simple alkali experiments. The problem is that it's a mean field description of the dynamics. So it cannot really reproduce an electronic transition. It can reproduce on average what is happening, but not the transition itself. If you force the system to start on one electronic state, and then you stop the dynamics and you say, okay, there will be a transition to this lower state, it does give the correct answer, but then you have to decide by hand how much of this energy difference you will give as kinetic energy to the alkali. So it's not very satisfactory for a molecular physics point of view. And so we looked for another method. So another method, this is an old one that we used because that was during David Bonomo's thesis. But I think it gives useful information, useful insight into the problems, and then we can work on from there. So the idea is you dress each helium atom with a wave function, which will describe the 0-point energy delocalization. This wave function is determined iteratively at the beginning, so for the equilibrium configuration, by solving the problem of one helium atom in the midfield of all the others around. And then it's kept frozen during the dynamics. So in that sense, it's similar to the frozen Gaussian wave packets from Heller, except it's not limited to be a Gaussian. It has some input from the anharmonicity and everything. The good thing is that then it's equivalent to running classical dynamics with effective potentials. So you can run almost as many atoms as you want. It's not difficult. The effective potentials being just original potentials that are convolved with the helium probability density. So just to show you that it can give a reasonable estimate, for instance, for the initial conditions, this would be the case of barium plus at a helium 1000 droplet. The barium plus, you can barely see, it's here in cyan color, light blue color at the center. And here is a density profile of the droplets. The DFT is the reference result. So the helium DFT, of course, is the black curve. And the one obtained with this method is the red curve. So it's a little bit too structured because it's classical after all, but it still makes a good job at reproducing this, the width of the distribution, for instance. And again, another check is looking at the absorption spectrum for barium plus 6s to 6p excitation. This is the top spectrum is inside bulk helium. The middle one is inside the droplet, it's Drabel's experiment. And the bottom one is what we get. So you see that the shifts are correct. What is missing is the quantum fluctuations, but we can add that by hand afterwards. Okay, and so from there on, the nice thing with ZPAD is that you can choose which type of dynamics you're going to use. So you can use mean field, like you were using in Helium Dft, but of course then you don't gain much. Or you can use trajectory surface hopping, like Mario was describing earlier. And in this case, for trajectory surface hopping, we use, again, a dim Hamiltonian, to which we add the atomic spin orbit. And this is an example. This is just gas phase. There's no helium there. But just to show you that everything that can be done with it, this is a neon cluster, in this case, 12 atom cluster. And the atoms are red when they get a charge of 1/2. They are blue when they are neutral. And so this is an initial configuration sampled amongst the different possibility for the neon 12 in the neutral state, and then it's ionized vertically. And here's the dynamics. And there's a lot of exchange of charge exchange during the dynamics, a lot of dissociation because the equilibrium distance in the neutral is van der Waals, so it's rather long distance, whereas in the ion, it's much shorter. So the ions are created with a lot of internal energy, which induces a lot of dissociation. Okay, and then now the same process studied inside a helium droplet. So that's an old calculation. There's only 100 helium atoms. And there is one cluster in the middle in red. It's no longer the same color code, I'm sorry. So it's just neon 4, which gets ionized. And you'll see one snapshot every 0.4 picoseconds. You see that there's a strong dissociation of the neon 4. This is here the neon 2+ core. And because of the recoil energy, it's the neon 2+ fragment actually also gets ejected. So that's a kind of dynamics that shows every one of the processes that can occur. Now David Bonomo has taken that again more recently with much more atoms, much more helium atoms, and you get all kinds of different interesting dynamics processes. I can discuss them later if you want. So I go back to the barium plus excited. There is a mistake here. It's 6s to 6p, sorry. And just to show you that with this method, we can describe and predict electronic transition. Here, it's initially excited to the highest electronic state, which is a sigma state. And you see that after about 0.1 picosecond, no, sorry. After 0.1 picosecond, there is a transition, almost 100% transition to the lower state, which is a pi3½ states, which can host an exciplex. And the reason why this happens is that initially the barium plus, this is different from an alkali atom, it sits at the center of the droplet, and the droplet is more or less spherical. So initially the energy levels are similar to the energy levels of an alkali, which means you have the J equals 3½ states together, and then the J equals 1½ state below here. But then as soon as it moves and it goes away from that quasi-spherical symmetry, then you go back to the usual sigma and pi interactions between the helium and the alkali. And the states separate into sigma here, pi3½ and pi1². So in between, there's this region where the two curves come very, very close to each other. And there's where there's a surface hop to the lower state. And this is what the dynamics follows. It initially follows the sigma state and then follows the pi3½ states. So as a quick summary. So we have seen for the helium time-independent DFT that it is very interesting because we can do both static properties, real-time dynamics. We can treat a large number of atoms. It's empirical, but because we use this functional, but it's also very accurate. We can also treat some anisotropy, since some of it with the diatomics in molecules model. But it cannot predict electronic transition. Another also side problem, or problem if you like, but is that it's expensive to run. I mean, it's, even can treat many atoms, there is a cost to it. And it's also limited to 0 Kelvin. The other approach that I showed today, the 0-point average dynamics, it's also very interesting, but it's really easy to use, but it's also very rather approximate. So we need to work a little more on it. One very interesting thing is that you can use surface hopping or other approaches that can help predict electronic transition, which was not for time-dependent DFT. And also, I didn't say, but it's run at the temperature of the droplets, which is 0.4 Kelvin. So if there are some, what do you say, that thermal effects, of course, 0.4 Kelvin is not much, but you know, it's helium and 0-point energy is important. You could see that. Another one, which I didn't talk about today, but it's something that we have started to study in the thesis of Wesley Untok, is MCTDH in Gaussian wave packet basis set with boson exchange. So that's heavy stuff to get started with. We have, with Wesley, we have done the TDH, so that's the easy part. We have started to go through MCTDH, and I know now that Uwe Mante in Bielefeld is also working along these lines. It would be very expensive from the computational point of view, but it's in principle exact. So you can go to maybe 50 atoms. You can use this exact result as a benchmark, and then you can design some approximations, for instance, with for the exchange correlation term, and be able to run with just mean field in this case, but having a correction for exchange correlation, which would be important. Thank you very much for your attention. Je suis dans les temps.
First of all, thank you very much for this nice, I would say, update about all those developments.
Yes.
I was wondering, you were talking at the end about the possibility to introduce three-body effects, but I thought that from the very beginning you are only considering a dim interaction. So why would you suddenly, you think that you need at the end something like related to the three-body potentials, or what is the message here when you say that you want to include them in your conclusion?
No, it's not really three bodies, it's exchange correlation. Right?
Because you talked about it was written, where was it? Somewhere here? Was it the previous slide? Yeah, maybe here, the possibility for simple three-body effects.
Ah, okay, yes, sorry, I didn't say it, but you read it faster than I could speak. No, that's a possibility for that is a point that we have encountered is when you treat an ion inside helium, of course, atom-atom is not really satisfactory, it's not enough, right? So at least you would like to introduce induced dipole interactions, for instance.
Mm-hmm.
In ZPAD, you can do it because it's atomic.
Mm-hmm.
With a DFT, I don't know how to do it so far. I mean, we're trying to work on it, but it's not
but you
so
would do it,
straightforward.
You would do it only for ions or also for the alkali atom? What I'm saying is that you have an ion, so I can imagine that indeed you can have two atoms interacting directly with a single ion, just because the range of the interaction is larger.
Mm-hmm.
And you would suggest that for alkali atoms, it is not necessary to include that particular effect?
Well, that particular effect is just a induced dipole created on each helium atom because of the presence of the charge.
Yeah,
so this is a big effect.
Okay, yeah, sure. Yeah.
For alkali atoms, they sit on the surface of the
that's
droplet.
Yeah,
so
okay,
maybe it's not
true.
so important. We take into account some of it using the diatomics in molecules, but
but when you look at the dynamics of the ionization of the rubidium, then you are left now with the rubidium plus. So that means that if you want to describe that dynamics, you would at some point also need to also include that effect, those three-body effects in your dynamics when you look at the photoionization.
Okay, if you want it to be exact, you should.
Yeah.
But what is interesting to the experimentalists is whether or not the rubidium will
be
slow down and turn
cluster.
around and come back.
Yeah, okay.
They don't really care what happens once it's come back.
Yes, okay.
So that part is correct, I think,
Yes.
because it happens at long range. I mean, when the rubidium is rather far from the droplet.
Yeah, okay.
So I think that part is correctly described.
Okay.
But in principle, yes, we should afterwards.
Okay, so it is just the goal, the motivation, which is different, which is when you do photoionization, you have the rubidium plus ion, which is or not ejected. This is the effect that you want to see. When you look at barium plus, you are actually relying on some kind of spectroscopy. And so you want that particular stage to be as exact as possible, then to describe. Okay.
Right.
These are the goal.
I talked about too many things, but it's because I wanted to stress the things that could be related to machine learning, and I didn't actually, but you saw it in red, right? So.
Okay. Stefan.
So thank you very much for the interesting talk. So coming back to these vortices, right? So in the results, you showed that the vortices appeared almost a bit like a nuisance, right? In the sense that they were disturbing the dynamics that was happening anyway.
Okay, you can see it as a nuisance or an attractor.
Yes. Yeah, exactly, right. And I was wondering, I mean, can one also use them as a resource, right? To get some results, some dynamics that one otherwise would not get. Yes,
exactly. Well, that's a very good point. Yes, that's what people are also, especially people coming from nuclear physics like Manuel Barranco and Matipi, they get very excited each time they see a vortex. So not only you can use them when you create them and you want to see what happens to the dynamics, but actually also when you have rather high energy collision, one atom entering a droplet, this can create vortices also inside the droplet. And so it's kind of fun to look for these vortices around. So yes, but there are some effects that can be used. And actually that's what, so they initially used vortice, they initially used doping with silver atoms, for instance, to visualize the vortices. But then they said, okay, then now that we know that they actually get attracted to the vortex lines, we can use these vortices to create these filament-shaped nano clusters or something like that. Right. Yes, exactly.
Thank you.
David.
Yeah, thanks. I really enjoy your talk. I've got a question about the DFT parts. So you're using some kind of free orbital DFT kind of method?
Yes, it's going to be slow, sorry.
Can you use also, I don't know, your like a Comshan method to using or let's say kind of molecular orbital, but with helium instead of electrons? I don't know if it's relevant to boson things. So instead of orbital free, some kind of description in terms of orbital. So I don't know if it's really relevant to that.
So actually, we don't have the Consham orbitals because it's bosons. Okay. So they all have it and still 0 Kelvin. So in principle, the reference, the kinetic energy term I was showing, is everyone has the same wave function. And that's why the kinetic energy term, 0 order kinetic energy term, is so simple.
Okay.
And then everything else is hidden in the functional.
But then when you doing some kind of excitation, you're starting to your let's say your wave function should have some kind of nodes or something like that. So is it going to work also when you use the simple kind of functional for the, I mean, description for the kinetic energy part?
Well, everything else is in the functional. So and maybe you have, okay, I can try to go back to it, but there's some cubic terms, there's some other terms I can introduce.
But in the in the exchange, what usually we call exchange correlation function, but yeah, there's some kinetic parts.
Yes.
Okay.
Yes, there's also some kinetic parts. It's taking into account all that. Everything here, it's there. So there's some square and cubic terms, and there's also, if you want everything to be correct, there's also the what they call the backflow part. So you see here some things that correspond to the kinetic energy, the gradients of the density. So I'm not a specialist from this thing, but that's what I understand from all their work, and that's why they could reproduce also the excitation curve of the the epsilon as a function of momentum for the very peculiar form for the superfluid helium, which is very different from any normal liquid. And they reproduce it up to a certain level of excitation. And we don't know exactly what the limit is, but if the excitations go really very high, you mean in the motion of the helium, of course, then maybe we are not so good.
Okay. Thank you. Yeah, that it's working because it's boson actually.
Yes, because it's boson.
So maybe we conclude this morning. So let us thank all the speakers again, please.
Thank you.
And I guess we go to lunch and we reconvene at 2 o'clock, if I'm right.